I'm going to take a slight diversion to fill in a few gaps about primitives and colors that we haven't fully explored yet. So let's look at first the primitives that we support and look at all the variants that we have, and then we'll talk a little more about color and how color is handled within WebGL. WebGL only supports a limited set of primitives, and in fact, even that limited set is even more limited from what desktop OpenGL used to provide. And it's very much keyed towards what is the most efficient thing that the hardware can do. One of the big advantages of OpenGL and certainly WebGL has been that it's close enough to the hardware that it can operate, still be easy to write a program, but operate very efficiently with existing hardware. And what hardware favors are just a very few primitives that can be rasterized very quickly. I mean, we talk in terms of millions of triangles, tens of millions of triangles per second, even on very low cost GPUs. So let's look at the primitives that are supported, and these are the names of the parameters that go in GL draw arrays. Remember, we send data to the GPU, and then we say how do we want that data rendered. And these are all the choices that you have. You can render them as points, so each vertex becomes one or more pixels. We can render it as lines, where each pair of vertices is interpreted as one line segment. So the first and the second form the first line segment, the third and the fourth the second, and so on. If we want to connect those lines segments, then we can use GL line strip that'll connect the first to the second to the third, and so on until it gets to the end. If we want to connect the last one back to the first, then we use GL line loop in draw arrays. And those are the basic point and line types. That's it. For polygons, the only polygon that's now supported is a triangle, and we have three forms to support a triangle. The first one is very straightforward, GL triangles, and what it does is take each successive three vertices in the buffer and output a triangle for each one. So the first, second, third of the first triangle, the fourth, fifth, and sixth of the second, and so on. And any odd number of triangles left at the end, modulo 3, are just discarded. The same thing with lines. If you have an odd number of vertices in there, it'll discard that last one. Now you have two other variants that are very important, both for modeling and both for the efficiency of rendering. What a line strip does is say, use the first three vertices to determine the first triangle. So let's say here's first, second, third, and then each successive vertex after that is coupled back to the previous two to form a new triangle. So if here's the fourth, it's coupled back to the one before it and the one before that to form this triangle, and then the next one in the left. So here's 1, 2, 3, 4. Here would be the fifth one, which would use this one and the one before it, and the one before it, and so on. So you can see that this is very efficient to form nice things that you might want to make a surface out of. And after the first triangle, every successive triangle only requires one vertex, rather than when you use triangles, each successive triangle would require three more vertices to be specified, even if two of them were used in common with a previous triangle. So in the limit, it's 3 times as efficient as is just using GL triangles, and many CAD packages will automatically output data as triangle strips. Variant on that is the triangle fan, where we keep the first vertex always fixed. The first three determine the first triangle, which is rendered. Then as we add successive vertices, the next vertex, so here would be the fourth one, would be coupled back one and back to the first vertex. So the first vertex appears in all the triangles that are rendered. So we get something that looks like this, looks like a fan. The example in the book that I use of this is the simple model of a sphere, where if you approximate a sphere by drawing equally spaced lines of longitude and latitude, or equal angle lines of latitude and longitude, you get a bunch of quadrilaterals for the most part, each of which going around the Earth for at a constant latitude will give you a triangle strip going around. But you have a problem at the poles because all of the lines of longitude meet at the poles, and so you wind up using a couple of triangle fans at the poles. So at the North Pole, you'd have something like this that went completely around, and similarly at the South Pole. So it's a good example of why you need both. Now WebGL only, as we said, only displays triangles. And what is it about triangles that we like so much? Well, there are three facts that make it important for a renderer and also important for a modeler. One is we don't want to have, consider polygons. We don't want to have a polygon where the edges cross, because then it starts getting very unclear about how we should render it. So even if you only had 4 vertices, as in the bottom left here, 1, 2, 3, 4, the lines that join them could cross, and then it gets very unclear if this is the way I want to fill it, or possibly some other way. And also just little questions like what's the inside and what's the outside. So this is a simple polygon is one in which the edges can't cross. A non-simple polygon is one for which they do. The second thing is the second point is we like objects that are convex. Convex simply means that if I take an object in no matter how many dimensions, and I take any 2 points in or on that object and I connect them, that line segment is entirely inside of that object. So a square, for example, is a very simple convex object. A triangle is always convex, which is what we like about it. A cube is convex, a sphere is convex. But if you have something like this star over here in the bottom right, if I pick a point, say over here, another one over here, the line segment joining them comes outside of the object, and that's not a convex object. The third property I'd like to have when we go to 3D is that when I define an object, all that object lies entirely in a plane. This is especially important when we deal with polygons. In 2D, it's very simple. I give you a bunch of vertices. They all lie on the same plane, and I could come up with a test for both convexity and simplicity. But in 3D, if I give you a set of vertices, I can always draw the edges because I can connect the first vertex to the second, the third to the fourth, and finally the last one back to the first. But it's very unclear what the interior is, because if those vertices are not all in the same plane, I don't have a mathematically well-defined interior. So now if I want to fill that, the notion of fill may not even exist, or at least there be a consistent definition of it. So what almost all rendering systems now do is say, we're only going to render triangles, and it's the job of the application program to tessellate, which means to break up that polygon into smaller polygons, usually triangles, and we call that triangulation. And I'll give you in a minute a simple algorithm for doing that, not necessarily the best one. Now, in more recent versions of OpenGL, starting with 4.1, it contains a tessellator, but that's not yet in WebGL, although there's code out there to tessellate general polygons, and I'll show you, as I said, one example of doing that. In fact, tessellation can get very, very complex if you start talking about polygons that have holes in their interior and all kinds of other little issues arise. So tessellation is not a simple thing, but there is a tessellator starting with 4.1. It's called a tessellation shader. Let's talk a little bit about the tests. The tests are conceptually simple. If you say, well, how do I get a simple polygon and check where their edges cross? Well, I could test every edge against every other edge, and that's a sort of, if I have n edges, that's an order n squared thing to do. So it's time consuming, and that's the reasons that graphic systems say, we're not going to do this because the time penalty is too great. We leave that up to the application programmers. So triangles, it's not, as we said, it's not a problem, so we don't need to worry about that kind of issue. Convexity, we can have a lot of tests for, again, by looking at edges, but once more, it's too time consuming, and so we're going to say it's up to the application to do that, and by just saying, oh, we're going to render as triangles, we don't have to deal with these problems. But then not all triangles are the same. So if I look at these four vertices, suppose I start with this quadrilateral, first, second, third, fourth vertices, and I say, well, how am I going to break that up into triangles so that I can render them? Well, there's two ways. I can draw this diagonal across and create two triangles, or I can draw the diagonal from the top to the bottom. These are not equal in terms of how they render. Long, thin triangles can be real problematic when you try and shade them and get smooth shading, because the difference in properties from one end is very different from the properties at the other end. In this case, we would much rather triangulate it by drawing the shorter diagonal and creating two triangles that are more closer to being an equilateral. Sort of the best thing you can hope for is an equilateral triangle, which is also equivalent to saying, I want to maximize the smallest angle in the triangle. If you think about that, since we know the angles have to sum up to 180 degrees, if I make the largest minimum angle, the best I can do is have an equilateral triangle, and those are the ones that will render best. If I give you a bunch of points, I go out there with something like a laser scanner, and I just get perhaps millions of points, and I want to form a triangular mesh that I could render. I want to get a good mesh with good triangles. There's something called the Delaunay triangulation, which in a mathematical sense will give you the best triangulation, because it will maximize the minimum angles of these triangles. We talk about that later in the book. But for now, let's just understand that we prefer to have triangles that are closer to being equilateral rather than long, thin triangles. Now here's a very simple but perhaps bad visually a triangulation scheme. If you knew the triangle was convex in the first place, I can do the following. I could start with what I'm doing here is making a triangle fan. I could start with the first vertex, go to the second and the third. Here's a little triangle, break that off. Now I've thrown away B. Now I can take the last vertex C, add on D, and so on, then throw away C, go on. This is just a triangle fan. Well, that'll work, but it won't work if you have a triangle which is not, a polygon which is not convex. So here's a non-convex or concave polygon, and here's a nice simple algorithm for doing it, maybe our first real algorithm of the class. And here's some intermediate stage. And suppose I start with this vertex VI, and I look at the vertex before it, so I'm circling it in a counterclockwise direction, which we'll see is usually what we want to do. So suppose here's VI minus vertex I minus 1, vertex VI plus 1. And suppose I go leftmost, that's going to be important here. So I start with the leftmost vertex and look at the vertices to the right and the left of it, and I get these two. Now if I try and break this triangle off, I've got a problem because this is not a convex object, and when I join these two vertices, it goes outside of the object. So what's a better algorithm? Well, here's a very nice recursive way, and you'll see I like to do little recursive algorithms. So let's say this is the leftmost one, and I start with that one. What if I find the leftmost vertex of all the ones that are left? So there's a sorting step that goes on here, and you computer scientists and engineers know the complexity of doing these kind of sorts. But generally, this will be a small sort. There won't be that many vertices in the polygon. Now look at what happens. I can always know, since this is the leftmost vertex, and this is actually the next leftmost, if I draw this edge here, it will always create two other triangles, and this edge cannot lie outside of the original polygon. So now I've formed two polygons that have fewer vertices than the first one, so I apply this algorithm recursively on both. So it's very simple to write recursively. Now I take this one, I take a vertex, the leftmost vertex, find the next leftmost one, and then split it again and split it again until eventually all I have are polygons with 3 vertices. Well, those are all triangles. They're automatically convex, and now I can render them all. So the point here is not so much that this is particularly the world's greatest algorithm, because it may not create the best triangles in the world, but that there exist algorithms to break up a general polygon, which may be non-convex, into a number of triangles, which will render. Okay, now let's go back and look at attributes, and I mostly want to look at color, but other attributes. Let's start with this. The traditional definition of an attribute is anything that determines the appearance of an object. So it's color, how wide the line is you draw it, whether you draw, if you're drawing the borders of a polygon, what kind of pattern do you use, or if you go inside and fill it, do you fill it with a solid color, or do you fill it with a pattern that's called a stipple pattern? Do you display the edges or not display the edges if you're filling the inside? There are modes where if I have a polygon, I only display the vertices as points. So all of these are attributes, how I want that polygon to appear. These, in older versions of the fixed function pipeline, all had parameters associated with them, or they were features that you could enable. You could enable stippling or disable stippling. You could set the pattern. You could set a flag that would say display the edges or not display the edges. All of that with the only one you'll probably get into is point size. All the others have been deprecated in modern OpenGL. You can use GL underscore point size in the shader to say how many pixels is a point going to be rendered in if you're using draw arrays with GL points. This will say how big you want those to appear. But other than that, you'll have to do all of this yourself, which we'll be doing as we go along. Now, let me look a little bit at color, both traditionally and how we use it. We're going to be using RGBA color. Now, what that means is usually is that on the output end, in terms of the hardware, there's usually 8 bits per component in the buffer. So a color buffer would have 8 bits for red, 8 bits for green, 8 bits for blue, which would mean that you could get colors, if we looked at them numerically, for each component going from 0 to 255. Or another way of looking at it is that if you have 2 to the 8th, 256 reds, 256 greens, and 256 blues, the total number of colors you get is 2 to the 24th, so like 4 million colors. If we look at them in terms of how we specify them within WebGL, we'll usually use we'll abstract it a step and say, look, I don't know or care how many bits are out there. I'm going to specify a color as going between 0 and 1 using floating point numbers to specify it, where 0 means none of that component and 1 means all of that component. One thing that's happened, gotten more important recently, is the use of more than 8 bits per color in many devices, and so this high definition color where you might have 12 or more bits per component is getting to be more important, and things like some of the recent even point and shoot cameras support high resolution color, which we may have time to talk about later. But that's the standard model. You have separate red, green, and blue components. Sometimes they're called, in terms of the hardware, red, green, and blue channels to give you the output. Historically, there was a mode called index color, which was supported in early versions of most graphic systems, where when you didn't have as much memory, because what RGB color forces you to have is enough memory, 3 bytes per pixel, to store that, and generally you'll have another 8 bits to store the opacity, so you use 32 bits, which is a nice number in our computers for each color. So you'll have, if you have a 1024 by 1024 display, you have something like 4 million bytes to store that single image in an uncompressed form. Now, when memory was more expensive and slower and less dense, you would have generally 8 bits to store a color. Well, that's not very good because you can do things, and there are lots of schemes still supported out there, where you break up that 8 bits into separate RG and B components, like 3 bits for one, 3 bits for another, and 2 bits for the third. That's not very good, but systems used to do that. What's more efficient way to do it is to argue this way, that if I only have 8 bits, it says I can display 256 colors at one time, and many images, especially when you're doing web-based stuff, really you don't need more than 256 colors at a time to give an adequate image. But what I want is the ability to choose from many colors. This is a very painting-like analogy where a artist or a painter would have a limited number of brushes. That would correspond to how many colors you could produce at one time, but you could mix an infinite number of colors from tubes of paints, and at any one time you say, which 256 do I want to use? Well, the digital equivalent of that is we have tables that say, for those 8 bits, it's a entry into a red lookup table, a green lookup table, and a blue lookup table. So at any time, I have 256 out of 2 to the 24th possible colors. So that is called index color. It's not a standard mode for the display of color now because we have so much memory, but it's very important later on when we start talking about imaging applications, where we start with something with a black and white image that will often have 256 shades of gray, but in order to see the information better, I'm going to convert those 256 shades of gray into colors out of my full 2 to the 24th possible colors, and that's called pseudo-coloring, and we'll talk about it later. But let's return now to RGB color and talk about how the color is applied, because our basic mode is we specify objects by their vertices, we specify attributes on a vertex by vertex basis, and then we send that out to the shaders. And what's going to happen? Well, if we do vertex colors, and I suppose I send a different color out for each vertex. So here's on the right is a cube, and what I've done is I've colored the 8 vertices with the 3 primary colors, red, green, and blue, and the 3 what are called complementary colors, cyan, magenta, and yellow. It's what I would get by adding together pairs out of red, green, and blue. So here's a yellow from red and green, and here's a magenta from blue, yellow. And the other 2 I get is white and black, and that's usually the 8 most easy to spot colors. So one way to do this is to use the rasterizer sort of automatically to interpolate between the vertex colors, and that's what you see what's going on here. And you may be able to detect a little bit that the rendering here, even though it's 6 faces for the cube, it's actually being rendered as 12 triangles, because all we can ultimately render are triangles. You might see that a little here and how the colors are being blended. So what's happening over here from the rasterizer is blending the vertex colors. Okay, so these 3 are yellow, green, and cyan. Cyan is blue plus green. And what it's doing now is averaging them by an interpolation scheme over this, and these, what you're seeing here, are the fragment colors. Likewise for the other faces. Here you're interpolating for this triangle, interpolates between red, white, and yellow. Okay. So this is done automatically. The alternative is this is called smooth shading, and smooth shading generally is the default in most systems. If you would rather display that cube with a solid color in each face, that's called flat shading, and we write our shaders so that the first vertex, for example, determines the color, or we send the color over as a uniform variable. There are a number of ways of doing that. Okay, so we can, ultimately, to summarize that, the colors are determined in the fragment shader, because the fragment shader is where we have to output a color, and we can output what comes in from the vertex shader. We can either interpolated or not interpolated, or we can send over a uniform variable that says this is the color I want you to use for this triangle, or I can do something like use texture mapping, which we'll be talking about later to say forget about vertex colors or not set any vertex colors and just use the texture to determine that. So you have a tremendous amount of control over how you do the coloring eventually, because the fragment shader can combine textures and vertex colors, or even generate colors within the fragment shader within code to determine what eventually goes out to color that fragment.